Let's draw a pH curve, a pH diagram. The pH diagram for a refrigeration cycle is pretty fun to draw. I like developing it together with students. So if I gave you just this curve, I need you to be at a point where you can draw a pH diagram based on our idealistic, our drawing that we made about the components of a refrigeration system, the basic components, basic 4 components. So I'm going to suggest to you a very easy starting point. We saw on our diagram, or we know about a refrigeration cycle, and we know that there's a high pressure and there's a low pressure. So we're looking at the axis here of pressure, and we're drawing a line for high pressure and low pressure. And that gives you a nice starting point to sort of anchor this chart. And how do we get from low pressure to high pressure? Well, typically we get from low pressure to high pressure through a compressor. So now you know that a compressor is going to start down here at low and it's going to go up to high. So we must do this for a compressor. But where does it start on the low pressure line? Do we pump liquid through a compressor? Do we pump a liquid gas mixture through a compressor? Do we do a little bit of both? Or do we pump a gas through a compressor? And the answer is we pump a gas through a compressor. So that's how you know where you're going to start. So let's take our low pressure line, and we better not pump liquid through a compressor. So we have to make sure we could start here, but we have to make sure that we're good and out of that liquid state. So we actually make sure that we superheat the steam, and that's called, this process right in here is called isobaric. Isobaric means, iso means same, baric means pressure. So this is isobaric heating. So this is to superheat the steam. And we know that we're in the gaseous state there. And then we take this through a compressor. So do we want to go like this and say compressor? Or do we want to go like this and say compressor? Let's look at the difference between these two lines. If we say it goes straight up, then that's ideal. We can say that, oh, we compressed, pressure went up, nothing else happened. But that's not actually what happens. When we compress, we actually put work in, right? We put work energy into the system. We pay for electricity to put work energy in. So what actually happens is enthalpy increases. So the enthalpy of the system increases. So this is actually our second point. So if we say this is 1 going into the compressor, then point 2 is actually here and has higher pressure, higher enthalpy when you got out of the compressor. And then you need to deheat this superheated steam. So our next step is deheating the superheated steam. And that it happens at a single pressure, single iso pressure, baric. And it is not a heating process. What happens is it cools. So as it is losing heat, what's happening first is a deheating process, and that is deheating that superheating steam. That's isobaric cooling. But that's not part of condensation yet. So then as soon as you turn everything into a liquid gas mixture, not all gas, then it is the process of condensing. So what's happening over here is it's condensing. It's going from a gaseous state down to a liquid state. Here, there's liquid plus gas, more gas than liquid. Here, there's liquid plus gas, more liquid than gas. So that's going through a condensing state, and that's in a heat exchanger that we call a condenser. And why does this happen? Why do we put a condenser there? In order to, this is the whole point, Q dot heat, we are going to expel the heat that we took from inside or from where the place we want to cool. We need to expel it so that we can go and get more. So that's good. We're expelling that heat energy to do that process all the way here to point 3, where this part, it's now completely liquid. So as it continues, and we design it so that it continues to lose its heat, even when it has become entirely liquid state. So when it's continuing to lose its heat in this state, it's called iso, so same, baric. You see that the same pressure, you're on the same pressure line, that high pressure line. That's isobaric cooling. It's deheating the superheated steam. All right, so that's also isobaric cooling. So then what happens now is it's a pretty cool liquid. So let's put on our temperatures here. This would be really hot working fluid here, right? And it started kind of warm. We made it really hot so that when I go through this T ambient, I can lose heat or distribute heat that I showed as Q into T ambient, and then that makes it just warm. But I don't want to take a working fluid that's just warm and put it into the place I'm trying to cool. If I'm trying to cool something, then I want it to be a really, really cold fluid that is going to go in and steal all that heat from that room. So to make a really, really cold fluid, I put it through an expansion valve. And because of the ideal gas laws, I'm not changing the volume. So V in equals V. Oh, sorry, I am changing the volume. V out much greater than V in. Whereas on a condenser, V in equals V out. That's a constant volume process. Here, obviously, the compressor. Obviously, V out is much smaller than V in. Anyway, so I'm expanding this, and because of the laws of thermodynamics, or sorry, the ideal gas laws, you have expansion is going to decrease the temperature considerably. So then now you're going to have cold, very cold temperature working fluid. And that process is called isenthalpic. Iso means same. Thalpic means enthalpy is staying the same. Isenthalpic expansion to the evaporation pressure, to or low pressure. So now I'm back down at the low pressure line. We call that, or I call that anyway, 0.4 on the curve. And now I have a very cold working fluid. I'm going to put that into the atmosphere that I want to chill. Looking for a color here. Now I want to chill, let's say this room. So I put this really cold fluid through and it's going to gain heat just because of the laws of thermodynamics. If I put something cold in a warmer environment, it's going to suck up that heat. And that's the whole point. That's what we want to do this for. We're doing this at a constant pressure. So an isobaric constant pressure evaporation. And let's just label what this device is. This is a heat exchanger, and this is called an evaporator. Gains heat. So here on our diagram, we saw that we have a low pressure side and we have a high pressure side. We started with the thermodynamic curve where we have liquid and gas and a gaseous state of a refrigerant going through the refrigeration cycle. We anchored ourselves by looking at where is it low pressure, where is it high pressure, and we thought through, what does a compressor do? Well, a compressor must be compressing something in a gaseous state, so we were able to anchor ourselves at point 1 down here and think through that entire thermodynamic cycle from 1, 2, 3, and 4. And that's the pH curve for the refrigeration cycle.